Welcome to the deep dive. Today we're looking at concrete. Specifically how its size, the size of a beam, changes its strength.
Right. It's not as simple as you might think, like bigger just equals proportionally stronger.
Exactly. So we've got this research paper, Size Effect in Concrete Beams, a numerical investigation. And basically, it uses computer models to explore this.
Yeah, combining simulations with established theories about how concrete actually breaks.
Our mission then is to figure out why bigger isn't just stronger, proportionally speaking, and what's going on, fundamentally when concrete fails.
And the key idea, really, is that as beams get larger, failure has more to do with cracks growing rather than just the basic material strength.
Okay, so classical strength ideas don't quite cut it for concrete.
Not entirely. Concrete's tricky. It's called quasi-brittle. It's somewhere between, say, glass that shatters instantly and steel that bends a lot.
Oh, okay.
So you need fracture mechanics, the science of how cracks initiate and, well, spread.
And that brings us to Bažant's size effect law, the BSL. What's the core idea there for you listening?
Well, Bažant's law, it sort of explains this shift. For small concrete samples, failure is mostly about hitting the material's inherent strength limit.
Right, where it first cracks.
Exactly. But as you scale things up, tiny, unavoidable flaws inside the concrete become much more important. Failure starts being driven by these flaws growing into bigger cracks.
So it moves from being about the material's base strength to being more about how these cracks propagate.
Precisely. From strength-dominated to fracture-dominated failure.
And this is linked to something called the fracture process zone, the FPZ. Sounds like damage happening before the main crack really goes.
That's a good way to put it, yeah. Just ahead of the tip of a major crack, you get this whole region where microcracks are forming, connecting, and this zone actually absorbs energy as it develops, which influences how the main crack eventually moves through the material. It's like the material preparing to fail, microscopically.
Okay. And the study, it wasn't just theory. They ran simulations, right?
Okay.
Bending tests on different beam sizes.
Yes, 5 different sizes, from pretty small, 75 millimeters deep, up to a meter deep. Quite a range.
Wow. And they even looked at the shape of the aggregates, the stones inside.
They did. They modeled 2 types, simple spheres and then more realistic kind of angular shapes.
RSA, realistic shape aggregate. Okay.
And they also modeled the concrete as non-uniform, paying special attention to that interfacial transition zone, the ITZ.
That boundary between the aggregate and the cement paste.
Exactly. It's often a bit weaker, more porous, so it's a likely spot for cracks to get started.
So what did the aggregate shape difference show? Did it matter much?
It did, interestingly. The beams with the realistic angular aggregates actually showed a slightly higher load-carrying capacity in the models.
Huh. Why is that? You might think sharp corners would be weak points.
Well, they can be stress concentrators, yes, starting cracks, but they also interlock better.
Ah, I see.
Which can make the crack path more tortuous, more complex, needing a bit more energy to break fully. Spheres, on the other hand, distribute stress more evenly initially.
And the overall failure behavior.
Yeah.
The load versus deflection. Did size change that too?
Absolutely. The simulations showed the larger beams failing more brittly. Meaning, after they hit their peak load, their strength dropped off much more sharply, more suddenly, compared to the smaller beams.
Okay, so less gradual failure. For you listening, that means a bigger beam might give less warning before it actually fails.
That's the implication, yeah. Smaller beams showed more softening, a more gradual decline in load capacity.
They also looked at fracture energy. Yeah, the energy needed to create a cracked surface. What happened there?
What was interesting is that the fracture energy generally increased with the beam size, but it seemed to plateau, kind of level off, for the largest beams they simulated.
So bigger beams need more total energy to break, but maybe the energy per new square inch of crack stabilizes.
Something like that, yeah. It suggests there might be a limit to that specific energy requirement in very large sections.
Now, these are computer models. How confident are we that this matches up with, real concrete beams?
They validated it. They compared their simulation results, the peak loads, the fracture energies, against published experimental data.
Yeah.
And the agreement was pretty good. Generally within, say, 3 to 8 or 9% difference, depending on the aggregate type and the specific measure. That gives us confidence the models are capturing the essential physics.
Right, that's quite close. So tying it all back to Bažant's size effect law, did the results support it?
Yes, very clearly. When they plotted their simulation data according to the format suggested by BSL, it confirmed the law's predictive power for this size effect.
It showed that transition you mentioned.
Exactly, you could see the behavior shifting. Smaller beams acting more based on material strength, while the larger beams trended towards what's called linear elastic fracture mechanics, or LEFM.
LEFM, meaning the failure is more like a brittle material, dominated by the energy needed to drive an existing sharp crack.
That's right, more predictable based purely on fracture properties in the large-scale limit.
Okay, so the big takeaway for you listening. Beam size really matters in concrete. It's not just simple scaling, it changes how it fails. Bažant's law captures this, and tiny details like aggregate shape and that fracture zone are surprisingly important.
Absolutely, and understanding this is critical for engineers designing structures. You can't just scale up a drawing, you have to account for these fracture mechanics principles to ensure things are safe and efficient, especially with today's massive projects.
Yeah, it really shows the hidden depths in something we see everywhere. It leaves me wondering, this study used medium-strength concrete. How different might things be for, say, ultra-high performance concrete?
That's a great question. In those materials, that ITZ, the interface zone, is much stronger.
Right. So would the size effect be less pronounced or maybe manifest differently? What new challenges pop up when predicting failure in enormous structures made of these advanced materials?
Definitely food for thought. Predicting failure in those scenarios is an active area of research.
Something to keep an eye on. Well, thanks for joining us on the Deep Dive.